Hey everybody, in this video we're going to talk about solving a system of nonlinear equations, problem type 1. So for this type of problem we have two equations that were given. X squared plus y squared equals 25 and y equals x plus 1. This first one, if you remember, is a circle centered at 0, 0 with a radius of 5. So I can go ahead and graph that. The next one is a line with a y-intercept of 1 and a slope of 1, so I go ahead and graph that. Now, where these two equations intersect are my solutions. And according to this graph, they're at 3, 4, and negative 4, negative 3. But what we can do is consider that maybe our graph isn't accurate, right? So, first thing we could do if we wanted to solve this graphically would be to just plug these points into each equation, and if they're true for if each line is true for each equation, or each point is true for each equation, then there'll be solutions. Or I could use algebra to make sure my solutions are correct. So I know y equals x plus 1, and I have a y in my first equation. So I'm going to use substitution. And for this first equation, we have x squared plus y squared, but y is equal to x plus 1 equals 25. This multiplies out to be x squared plus 2x plus 1, and then we still have this x squared to bring down, and it's equal to 25. After some combining like terms, we get 2x squared plus 2x, and then I'm going to also subtract 25 from both sides to get negative 24 equals 0. In order to solve this quadratic, I could do the quadratic formula, but the first thing to check is to see if it factors, because if it factors, it's a little simpler than quadratic formula. This is 2x squared plus x minus 12 equals 0. So 2 times x squared plus x minus 12 factors into x plus 4 times x minus 3. So now I can set each factor to 0 equal to 0, and I get x equals negative 4. Guess what? That's one of my solutions I think I'm supposed to get. And x equals 3. There's another one. So how do I solve for this? Well, I've solved for x, but I need to solve for y. And the second equation is easiest to find out what y is. Y is equal to x plus 1, so I plug in negative 4 in this case for x, and I get negative 3 for y. So negative 4, negative 3 is algebraically a solution. It also is a solution graphically. The next point at x equals 3, y is going to equal x, or 3 plus 1, so y should equal 4. This is at 3 and 4. And that's where my other solution was there. So that is one example about solving nonlinear equations. So let's take a look at this one, and this one kind of teaches us why we need to be careful about graphing solutions. So I see here from this graph that I have two solutions. Okay. I also see that if I multiply, this is equation 1 and this is equation 2. And if I multiply equation 2 by negative 1, I'm going to get negative 5x plus y equals negative 6. I'm going to go ahead and I'm going to add equation 1, which is x cubed minus y equals 2x. So when I add these together, I eliminated a variable. So this problem used elimination. So my three methods for solving these problems are graphically, substitution, which we did in the last example, and then elimination. Negative 5x plus x cubed, I can't really add those together, except for just to say it's x cubed minus 5x, and that's equal to 2x minus 6. Let's get everything onto one side by subtracting 2x and adding 6, and I get x cubed minus 7x plus 6 equals 0. How do I find zeros of polynomials? I have to think about the possible rational zeros, right? That was the p over q thing, which that happens to be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. I have previous videos on that. If that's getting you confused, it would be finding rational zeros of a polynomial. And so I can choose some of these to divide out using synthetic division, if you remember that. Now, based off the graph, this should be a 1 here. Based off the graph, I think I'm going to have a 0 at 1, so let's go ahead and test and see if 1 is an actual 0. And now, it's not a 0 of these polynomials, right? It's a 0 of the combination of polynomials, which is the intersection. So we think 1 is the intersection. So we do the synthetic division. Our coefficients are 1, 0, negative 7, and 6. Bring down the 1. 1 times 1 is 1. I'm adding these together. 0 plus 1 is 1. 1 times 1 is 1. Negative 7 plus 1 is negative 6. Times 1 is negative 6. When I add those together, I do get 0. So that means that so far, this polynomial factors into x minus 1 times my quotient, which is x squared plus x minus 6. And then this factors into x minus 1 times x minus 2 times x plus 3. So from here, this is all equal to 0. I would suspect to get x equal 1, which I did get here. And then I would suspect to get a solution of x equals 2, which I did get for this solution. But then I get a third solution at x equals negative 3. If we look at this graph, this keeps going on forever, and so does this line. So they're eventually going to meet somewhere way down here. And I find this y value the same way I found the other ones. In the last example, I plug in negative 3 for x into either equation, and I solve for y. So this is negative 15. I'm going to subtract 6 from both sides and add y to both sides. So negative 15 minus 6 equals y, or negative 21 equals y. So you can see why we didn't see this on the graph, because that's way, way, way down there. So I also have an extra solution at negative 3 and negative 21. And I want you to go ahead and go through these two x values and make sure you get the y value of 4 when you plug in 2 for x and negative 1 when you plug in a positive 1 for x. So those are some examples of solving systems of nonlinear equations.